It's a two-part problem. The first problem is the equation of continuity, that A1 V1 is equal to A2 V2. So V2 is A1 V1 over A2. This makes A1 20, A2 10. It's the same reason why I don't convert to square meters as I did in the other one. V1 is 4. So the bottom velocity is 8 meters per second. When I do problems like this, the thing that I do is I take care of the h equals 0 and I set it to be the lowest most point in the problem. This means that h2 is equal to 0 and h1 is equal to 20. So I'm allowed to zero that out. I'm looking for P2, and I'm looking more specifically for P2 in atmospheres. And what I'm going to do is I'm going to point out the pothole that a lot of students fall in. P1 is rho g h1 plus 1/2 rho v1 squared minus 1/2 rho v2 squared. And if I haven't said so, the density of the fluid is water. And so we get this. But the other thing that I'm going to do is I am going to divide what's in the parentheses by 1.013 times 10 to the 5th newtons per meter squared per atmosphere. And why is that? And this is the pothole. Rho gh and rho v squared both kick out newtons per meter squared. Their natural units are newtons per meter squared, but I asked for the units in atmospheres, which means that this term, and that term must be divided by that number for atmospheres to get kicked out. P1 is already in atmospheres because I said so, so I don't have to convert that one. If I had asked for newtons per meter squared and I had given that in atmospheres, I would have had to multiply that by the number and I would leave those three alone. So in this particular case, it's 3 plus so I get 4.7 atmospheres. And so that's a very simple fluids problem. It's a plug-and-chugger's dream. It's awesome. Yes, it is. To the person who said, is it really? Yes, thank you. Yes.
Can you just go over what each, like the P1, rho, GH, what each of those are in that equation? Like what is?
You mean do the unit work for that?
No, not just you don't work, like what is, so for me, like, I don't know, I'm just confused on like what everything is that's in that.
Okay.
Like I get that it's pressure, and then is that pressure again, but with
But it's pressure. Pressure comes from. There are three. Well, there's pressure, and then there's contributors to pressure.
Okay, so are the other two contributors?
Yeah, those two are contributors. This is a potential contributor. It's the same as that one. A potential contributor due to height. And then a pressure kinetic contributor. I don't know if contributor is spelled with an E or an O. That's not, I think it's an O. That's not the point. But Bernoulli's equation basically is going after the fact that pressure comes from, well, pressure has major contributors, a height contributor and a kinetic contributor. And so those are the two things. So yeah, a lot of times what I do is I write it like this. Pressure, potential, and kinetic. All three. And so I write them together. And so that is a simple Bernoulli's equation. The thing that I'm going to do right now is the last bit. Yay, last bit before we really just munch on problems. Are oscillators or pendulums. And I think what he's going to do is he's just going to have, well, I'm not sure what he's going to do. But there is what we call simple and spring. For simple, it's 2 pi L over G. For spring, it's 2 pi M over K. And when you get these, the simple pendulum is based on the length of the pendulum and gravity. So it's L and G dependent, and most importantly, it is mass independent. Where length, if you change the length of the simple pendulum, the period changes. If you change gravity, the pendulum's period changes. But if you change the mass at the end of the pendulum, it's not going to change anything. For the spring pendulum, what you notice is that it's M and K dependent. You can change the mass and change the period. You can change the K and you can change the period. But it is G and X independent. And the other thing that I want to show is that it is theta and M dependent. So what happens is that no matter what angle you start this thing out, it will not change the period of the pendulum. If it's a spring pendulum, gravity will not change the period. And I need to tweet somebody. Hold on. All right. So the big thing about this is one of the equations that I would also know is that t divided by n is period, where that little t is total time. N is the number of oscillations. So what we have here is take the total time divided by the number of oscillations and we get the period. In something like this, we could have a simple pendulum, and if he doesn't specify gravity, we're on Earth, which means that G is equal to 9.8. How long must it be for it to oscillate 46 times in 123 seconds? So how long will the simple pendulum have to be if it oscillates 46 times in 123 seconds? So starting from this, I'm looking for L. I'd square it. And then solve for L. So L is t squared over 4 pi squared. That comes down, G comes up. Now the thing that I don't have is the period, but I do know that the period is t divided by n, so this becomes little t squared G over 4 pi squared n. So it's 123 squared, 9.8, 4 pi squared, 46. And my thing says 81.6 meters. A rather long pendulum, but it just proves the technique. And the thing about the alphabet soup mode is that you don't, you can take these letters and you can solve for any of the variables that you want. When I went from here to there, I squared both sides. So the t becomes t squared, 2 pi becomes 4 pi squared, and the square root of L over G becomes L over G. Question?
Yeah, okay, since t is equal to, the time over the number of oscillations.
Yeah.
Should it be, like, why wouldn't it be t squared over n t squared? Like, why did t squared over n squared?
Oh, crud. Thank you. So now it's a much better number. It's 2.
Yeah.
1.77. I knew it felt a little bit long, but that was it. And thank you for pointing that out. Never trust an old man. So we could do the same things with spring pendulums, but it's the same technique. It's all him giving you several of the variables, and then you got to solve for one. So what we're going to do in the last half hour is we're just going to do problems and just slam through stuff. So I would be happy to take your questions, and we can do more problems tomorrow, or at 9 a.m. in the Weir Hall. So questions, or do you want me to just pick stuff? In blue, hold on. We're having discussions. What's the question? I thought you had something. Okay. Yes.
There's one on the north that looks like a ball with a traffic light. I think it was chapter 9,
Problem 9, chapter 19. Oh, please let me remember to bring it up. Yeah, let me borrow. I didn't bring paper of any kind, including the book. Oh, here it is. Chapter 9, number 19.
Yeah.
Ooh, all right. And get your book back from me because I steal stuff. So 19 is this guy. So a traffic light hangs from the pole. This is a really good problem. But the thing about it, I think that finding the tension in the horizontal cable CD is a worthwhile test problem. I think that the force exerted on the pivot or by the pivot A is a little bit overkill. That I think that the first part is a legitimate test question, but the second part is overkill. We can work on it, and I'll show you the parts. But the second part, actually, that's not that bad either. But let me show you what's going on. Yeah, it's the first. It's the setting up of the torque that's the issue.
Yeah.
So we have a bar, and there's the pivot point, and we're going to choose the pivot point as the rotation point. This is the wall. That is C, D, B, and M. They give you theta, they give you Y, and they give you the length of the pole. All right. So they give you this distance here, they give you that angle there, and then they give you, I don't bring a lot of things. They give you this distance here, which I will call L. So that is L. So I know this one, and that. Oh, and I know the mass of the bar, and this is the mass of the light. The mass of the bar is at its center of mass, so obviously its distance from there to there is L over 2. Now, what's interesting about this is we can, obviously, what's the one thing that we know? It's not doing anything, and thank goodness for that. So the sum of the torques is equal to 0. Now, how I would pick my rotation point is I would pick it wisely, and since that is the tension that we're looking for, what I'm going to do is I'm going to choose that point A as the rotation point. because I know ML, I know MB, I know tension, I know all the quantities that I need in order to get the necessary force. So what I'm going to do, there are a couple of things that you can do to figure this out, but what I'm going to do, the way that I do this, is at the very beginning of the discussion on torque. Let me find that example. I think it's the next one. Come on, show me. So of course on my notes. It's the one. It's the part in this lecture where I talked about you've got to find the perpendicular force to the rotation bar. And so what I'm going to do is I'm going to take this and I'm going to rotate it like that. Because what I'm going to do is I'm going to find those perpendicular forces to the bar. And I've rotated the bar. I know these distances. We have one of two choices to make. We either do this, or what we do is we find the distances from the forces to its axis. And what I like to do is I like to just change it to this. If I rotated the bar like this, and I said that force was an angle, that force was at an angle, and that force was an angle, the first thing that you would do is rotate it or find the vertical components to the bar. Oh. There we go. So instead of looking at it like this, I'm going to look at it like this, where I'm going to find those vertical to the bar components of this. And that's the procedure. Now the first torque, anything involving A, the forces of the hinge, they're all 0. The next thing that I need to do is I need to do a little bit of geometry play. And let's say I do this. If that's theta, that's phi, and phi is equal to 180 minus theta, because that's a right triangle. If that angle is phi, then that angle is phi. If that angle is phi, then that angle is phi, which makes that angle there theta and theta. So those are some geometry things. Now the three forces I've got to deal with are MBG, and I've got to work with these horizontal components. So in this I've got the force side, the theta angle, or I'm sorry, hold on, let me change this. For this one and this one, these are the triangles that I set up. That's theta. That's the force side. That's the force that's perpendicular side. So cosine of theta is F perpendicular divided by F. So F perpendicular is F cosine theta. I'm expanding on this one and that one. Those are the triangles that I'm working on. So in the case of MB, it is MBG cosine theta. In the case of ML, it's MLG cosine theta. Now for T sub y, if that's theta, that is theta. So the sine of theta will be Ty over T, and T sine theta is Ty. So the angles are set up a little bit different. Here, Ty is the opposite side to theta. Here, it's the adjacent side to theta. So that's why that sine and those two are cosine. So this becomes Ty sine of theta. Now it gets a little bit easier. For MBG, the mass of the bar, the distance from the pivot point to the force is L over 2. The distance from there to there for MLG is the distance of the full bar. Now, this distance for this guy is just a wee bit tricky. Not tricky, but I only have y and I have theta. And I'm looking for this length here. The sine of theta is opposite y over this r that I'm looking for. And the r is from there to there. Or it's the length AD. So RAD is y over sine of theta. So this is interesting. It's y over sine of theta. And what you can see here is that those signs cancel. Now we got to use the right-hand rule to determine the values. For those two, they're both to the right and they're both down. So to the right, in order to get the fingers to bend down, I flip over. The thumb goes into the page. So those two are negative. For this one, it's to the right. It's up the page, the thumb points out or positive. Now, since we're so short on time, and I didn't have, in my class when I cover the right-hand rule, we talk about this for like a half an hour. What you can also do is, if you think that this force is going to cause the bar to rotate counterclockwise, mark it positive. If you think that the rotation is going to cause a clockwise rotation, then you mark it negative. So you can do it that way, or you can use the right-hand rule. With practice, I don't even think about the right-hand rule. I just do it, and then if it comes out of the page, it's positive, and into the page, it's negative. So I'm all looking for t. And this ty, the other thing that I can do for this ty is that the t is the hypotenuse side. I can also say that sine of theta is ty over t. So ty, I'm going to get a sine theta back. Oh, wait, that's it. Hold on. I already did it. That's not a ty, that's a t. The ty is t sine theta. So there it goes. So I've already done the substitution. Now solving for t, L over 2 mb g cosine theta plus L mlg cosine theta is equal to yt, and that's it. So L mb g cosine theta over 2 plus L mlg cosine theta divided by y is equal to t. Now, to clean this up really quick, the L, the G, the cosine theta get kicked out. We have a 2y, or no, just a y. And then I'm left with mb over 2 plus ml. And interestingly enough, you could plug this in and you could get the answer. Plug the numbers in and then you go on from there. But the thing that I want to point out is a lot of people, I can hear, like, when I do these lectures, I can hear the audience go. And what I really like is when questions, like someone asks a question and someone in earshot hears it and then answers it for me. I really love this community involvement. But a lot of time, this is kind of a lot of problem. And this is one of the reasons why I don't think a problem like this would be on the test. I think a standard torque bar would be on the test. But let me show you a technique. You look at this and you go, how can this be possibly right? Well, L's units are in meters. Y's units are in meters. Gravity is in meters per second squared. Cosine theta, I don't care. It's a number. Mass and mass will give you more mass, which is kilograms. That cancels. So the unit that I get out of this is a Newton. Newton is a unit of force, or tension is a Newton. So the units do check out. There may be a number dropped here or there, but the core equation is correct. Question?
So basically when you solve the torques of A
Mm-hmm.
equal to 0, you made A 0, I understood that. And then you take 3 different places to solve the torques, basically?
No, what I did is I had 3 places because I had 3 torques.
Yeah.
Now, the forces, I had to play the trig game with it. But I didn't have to mess with the distances. The distance from there to there is L over 2. From there to there, L. And from there to there, this y over sine theta. And so that there were no multiple origins.
No, I meant forces.
Yes, correct. Because there were 3 forces outside of A. Therefore, there were 3 torques rotating about A. 3 forces, 3 torques. Okay. So we still have 7 minutes. Or if you want to. I mean. So any other questions? Okay. All right. If there are no further questions, You can come up to me and talk to me later. But I will take cash. Cash works always. My Venmo account, if you came in late, is at Vance_Eschenberg. And $20.